Hello everyone. In this part of the lecture, we'll start discussing a new topic called principal strains, and it is an extremely important topic, not only from the point of view of examination and for our coursework, but from a professional engineering perspective also. So what do we mean by principal strains? In order to motivate that discussion, what we'll do is we'll go back to what we had discussed in the context of engineering strain. Alright, so if you quickly go back to one of the previous slides, you note this very important formula which I had highlighted earlier. So this was our compact formula for the engineering strain, and we'll start our discussion in relation to this. But before we go about doing that, you please note that this expression written in terms in this compact form, the n hat transpose dot epsilon, the strain tensor dotted with the n hat, this thing is basically the same thing as, if we go back one slide more, you see this thing is exactly that, and that is in index notation like this: nij epsilon ij. So if we go back, I'll write down this again. All right, and I also note that this is exactly equivalent to ni nj epsilon ij. You please note that, and this is very useful, that when you are writing in the compact notation, the order in which you are writing the terms, it really matters. Okay, you're not free to write them in any order you wish. However, when you're writing in index notation, there is no such restriction. You can write them in any order as you please. Okay, so this is just like simple algebraic manipulation. Okay, now coming back to the physical discussion, why it is so important, professionally speaking, from a real engineering perspective. You see, this is the engineering strain. Okay, and what we had discussed earlier was that if you sit at a particular point within the three-dimensional body and you are asked to find out the engineering strain along a particular direction given by this unit vector, then you have to use this formula. That is fine. So if you are given a state of strain and as well as you are given a certain direction, then you can find out the value of the engineering strain. However, suppose one asks the question, the very important question, that okay, there might be, sitting at a particular point, there may be an infinite number of directions around it. Now, along which direction should we look such that the engineering strain becomes a maximum? I repeat my question. We are sitting at a particular point and we are free to look at any particular direction. We set the direction, we can find out the engineering strain. But what about the question that among all these various directions denoted by various values of this n unit vector, which is that direction along which we get the maximum value of the engineering strain, and what is that value of the maximum engineering strain? So that question is answered within this purview of principal strains. So that kind of maximum value is referred to as the principal strain, and the directions along which those values are obtained, those maximum values or the principal values of the strains are obtained, they are referred to as the principal axis of strain. So how can we find out, how can we go about finding those directions and those values? That is the purpose here. Now there are different ways of proceeding here, but as in the previous years, the method that I will adopt is to proceed by taking full help of the index notation. Now as I proceed with the various steps here, you may find it a little bit difficult to follow because most of you are not that familiar with index notation, and please note that even though from a purely examination point of view, we will not be asking you questions to derive things like that based on the index notation, because as third year students, we don't expect you to be experts on index notation. But people who have some interest to pursue higher studies should note down these steps carefully, because it will be useful later on. Okay, so our question is, how can we maximize this value of this engineering strain, or more importantly, how can we find out along which direction the maximum value of this engineering strain will be obtained? Okay, so this is basically an extremization problem or a maximization problem, but there is a little bit of a restriction. We have to note this. This is very, very important. That restriction is, you are free to find out the direction with one restriction, that direction, the given by the ni, should be such that it is a unit vector. I repeat, you are free to find out the direction along which the engineering strain is maximized, with the restriction that the direction you find out, the direction vector you find out, that should be a unit vector. Because you note that by definition, what the way that we have proceeded and arrived at this formula here, this ni and nj, they are the unit vectors. So that fact has to be preserved in our derivation. So very formally speaking, mathematically, this kind of extremization problem is a constrained extremization problem. Is a constrained extremization problem. Let me write that down. Where the constraint is being this thing should be equal to 0, or ni should be equal to 0. You understand that this is just nothing but the dot product. Okay, all right. Now I have written this as as a transpose, but in the compact notation it doesn't really matter here. So had I written this purely as vectors or matrices, then this transpose matters. Otherwise, it really doesn't matter. Okay. Now, how can we set up the problem? Okay, so we want to maximize the epsilon e. So if we want to maximize the epsilon e with respect to the variation of what? With respect to the variation of this ni. So let me write that down. Now I don't want to use either the ni or the nj. I want to keep it generic, and I will write this as nk. All right. Now if I just set this thing equal to 0, it is going to be completely wrong. Why wrong? Because here the constraint is not imposed. Which constraint? This constraint, that it should be a unit vector. That constraint is not imposed here. So I cannot naively write like this. Rather, what I have to write, and you'll perhaps remember this from your first year mathematics, that I have to write this statement with the extra term here So what have I done here? So you see, this is my extra condition, the 1 minus nkk That is, so you see here the way that I've written it, I might as well write this as k, doesn't matter. I can write it as np np nq nq, doesn't matter, because this is not a free index, this is a dummy index. I can use any letter here. There's no need to write this as I, it will only create confusion with this I. So I'm using the nk here. Okay, now this is the original engineering strain, and this is my constraint. What is this lambda? I'm sure many of you will recognize that this is nothing but the Lagrange multiplier. This kind of a multiplier is used to set up our constraint extremization problem. So this is the thing that I want to extremize now. It cannot be just this thing, because I have to satisfy this constraint also. So this is like the so now the constraint is included here, and this L is like my objective function, and this is what I'm going to try to extremize. Del L del nk, that is what should be equal to 0. This is the proper extremization statement. Okay, so let me go to the next page and proceed with the actual steps. So I'm just repeating whatever I had written for the capital L earlier. This is equal to 0. Now I'm going to substitute the expression for the epsilon I here, which is nothing but ni nj epsilon ij, and here you note that I have minus lambda del nk of basically the nk square. Okay, now so this term is very easy. You can understand that in the next step I'm going to write this as minus 2 lambda nk, no problem there. But this one is a little bit tricky. You take this one by one. First of all, you tell me what will be the derivative. So you can think of it like three things clubbed together. We are going to take the derivative of this using the chain rule. So first of all, you tell me what should be del epsilon ij del nk. You think for a moment, should it not be equal to 0? The epsilon ij by itself does not depend on the unit vector. The epsilon ij, sure, epsilon e depends on the unit vector, but the epsilon ij, that is just the state of strain at a particular point. So that has nothing to do with the unit vector that you are choosing to look at. So the derivative of the epsilon ij with respect to the unit vector, that is equal to 0. So you don't have to, this is like a constant as far as this partial derivative is concerned. So you may as well take this out. So let's do that. Now I want to use the chain rule here and write this like this: ni nj plus epsilon ij, or I can just take this thing as common. Ni del nj del nk. You please note that I am not arbitrarily writing this. I am being very careful while writing these terms. Although it may seem so simple, but there is a little bit of an understanding involved here. And this one I can just write this as minus twice lambda nk. No problem here. Okay. Now we have to use the proper understanding. This is a crucial step. We have to find out the answer for this del ni del nk. it seems deceptively simple. It is simple, but we have to be a little bit careful here. So you see, suppose instead of the ni we had nk here. Suppose we were very fortunate that somehow there was an nk present. In that case, this would have been simply 1. Similarly, instead of the j here, somehow by some good luck we had k here, then this entire thing would have been 1. Unfortunately, it is not present, but we have a little implement or a little equipment in our hand to convert this ni to a nk, and that is by the use of the Kronecker delta. So what we'll do is I can write this nj here, otherwise the thing will look cluttered. So this is del nk, and this ni I will write as nk delta ik, where, going by our mathematical preliminaries, we are using the substitution power of the Kronecker delta. You understand that the resulting entity from this is nothing but ni. Nk delta ik is nothing but ni itself. Similar trick I can use for this next term. Again, I will write this as nk and adjust by the substitution power of the Kronecker delta. So this is delta jk, close bracket, minus 2 lambda nk. Okay, now this thing is no longer difficult. This is simply nj. Now the partial derivative of nk with respect to nk is simply 1. All that we are left with is this constant like quantity, which is the delta ik. We write it. Similarly, from the next one we have this n1 here, and this delta nk that is 1. We are just left with this constant like thing, which is the delta jk, and minus twice lambda nk is equal to 0. Now you see, we are again going to use the substitution power of this Kronecker delta ik, and this time if I multiply this out, what is going to be substituted? You see, in this thing there is no I, there is no k, so this one has no power over this, but here you see there is a I. So whatever this I is, it will be substituted by the other index k. So this one will become epsilon kj nj. So whatever the index was common with the Kronecker delta, that gets replaced by the other index which is present in the Kronecker delta, which is k here. So that k comes in place of the I here. Okay. Similarly, here we have delta jk. It is the j which is common this time. So this j in the epsilon ij will be replaced by the other index which is present in the Kronecker delta, which is k. So this j will become a k. So epsilon I k and this ni from here, minus twice lambda nk is equal to 0. Okay. Now you see, this is kj nj, this is epsilon ik ni. Now let me use the symmetry property of the strain tensor. So what I'll do is, I'll write this as epsilon jk nj. This one I'll leave as it is. Since epsilon kj is equal to epsilon jk, going by the symmetry property. Okay. Now you see, in this first term, the j is the repeated index. Okay, the j is the repeated index. Because this is a repeated index, it is also like the dummy index. So instead of j, I can write this as p. So it doesn't really matter because it is repeated, it is not a free index. So I can as well write this as epsilon pk np. Similarly, in the second term, I have this I as repeated, and because it is repeated, it is a dummy index, so I can replace the I again by p. I am very much free to do so. So again, this one will also become epsilon pk np. So here also I have epsilon pk np, here also I have epsilon pk np. So in the next page, I can write this as epsilon pk nk, epsilon pk, sorry, this should be np plus epsilon pk np minus twice lambda nk. So the reason that we state here is that replacing the dummy indices j and I by p. So what we'll end up with is twice epsilon pk np minus twice lambda nk is equal to 0. So the twice cancels out, and what we are left with is epsilon pk np minus lambda nk. Now what we'll do is we'll once more use the power of the Kronecker delta to make this nk to be np, and we'll take the np common. That is the motivation. So this is np minus lambda delta pk np, and in the next step we'll take this as common. Sorry, this should be a delta. Pk minus lambda delta pk np. Okay, now you see, starting from this step to whatever we have proceeded, this is like a full-on use of the index notation. And again, I repeat that at least for your examination purposes, we are not going to test you on these kinds of skills. Okay, this is only for the in order to make this, to keep this derivation relatively shorter, we have used this index notation. Otherwise, you note that in full length, if you had to write all the indexes in full form, in fully expanded form, it would have taken a lot of space and time. Without going into much further discussion, we can I'll quickly write this down, that this statement that I have written in the index notation, this is perfectly equivalent in matrix representation like this. You check one by one this epsilon pk, there is nothing stopping me from writing this in this matrix form. The corresponding matrix form for the Kronecker delta is nothing but the unitary matrix or the identity matrix, and this thing is multiplied by the, so I don't need this dot in this matrix representation. I can remove this. Had I written this in the compact or vector notation, I would have needed that. So I have this thing. Okay, so what am I basically doing? So suppose you had to write this down in a computer, what would you do? So this thing is perfectly equivalent to this. Epsilon 1 1 minus lambda epsilon 1 2 epsilon 1 3 epsilon 1 2 epsilon 2 2 minus lambda epsilon 2 3 epsilon 1 3 epsilon 2 3 and epsilon 3 3 minus lambda. Sorry. Okay, so whatever we have written here, this is the exact full version of this in the more familiar matrix form that that you know. Now, just for a quick correspondence, this n hat, this vector, this unit vector, it has the components of n1, n2, and n3. Now, this statement that we are obtaining, this is a system of linear equations, and you see that this is the classic form of an eigenvalue problem, which you are familiar with from your first year engineering mathematics days. Now, in order for this entire equation to have non-trivial solution, what you will need, you know the answer. You have to set the determinant of this matrix to be equal to 0. So going to the next page, for non-trivial solutions, we must have epsilon 1 1 minus lambda epsilon 1 2 epsilon 1 3 epsilon 1 2 epsilon 2 2 minus lambda epsilon 2 3 epsilon 1 3 epsilon 2 3 and epsilon 3 3 minus lambda. The determinant of that, please note that I am no longer writing this like a matrix, rather I am taking the determinant of this, that should be equal to 0. So this equation, the equation that you will obtain from by taking this determinant, that will give you the equation which will provide you with the extreme values or the principal the extreme values of the strains or the principal values of the strains. And you note what are we getting here? So this equation will be a cubic equation in terms of this lambda. Okay, it will be a cubic equation in terms of this lambda, and correspondingly will end up with 3 roots. So those 3 roots will provide you with the maximum possible values of the strains, and they will be referred to as the principal strains. Now, going back to our discussion of the eigenvalues, corresponding to each such root of the lambda, you will end up with a set of n1, n2, and n3. So suppose your roots are lambda, let's say lambda a, lambda b, and lambda c. Then corresponding to lambda a, you will have one set of n1, n2, n3. Corresponding to lambda b, you will have n1, n2, n3, and finally corresponding to lambda c, you will have the n1, n2, and n3. Okay, so what we'll put this down in writing, that the roots of the above equation that is the 3 values of lambda will be the extreme values that we are looking for. Will be the extreme values of the engineering strain, and so these, please note that these extreme values of the lambdas, so these are like the eigenvalues. These are the eigenvalues, and corresponding to each such extreme value, we can find a set of n1, n2, I think better written as a vector, a set of n1, n2 and n3. It is extremely important to note that please do not have this misconception. That's what I'm trying to emphasize here. It's not that you are getting 3 values of lambda and corresponding to those 3 values, these are the n1, n2 and 3. No, you get 3 values corresponding to each lambda. You will get 3 values of these 3 values, n1, n2 and 3. So first answer, so first, that's what I meant. So suppose your first root is lambda a. Correspond to that lambda a, you will get one set of this n1, n2 and 3. You change the value of lambda b, go back to the eigenvalue problem and try to find out the eigenvectors. So these are the eigenvectors themselves. You will get another set of n1, n2 and 3. You go to the lambda c, the third root, you will get another set of n1, n2 and n3. This is extremely important. So these are the will be referred to as eigenvectors. Okay. 3 such sets. You will obtain 3 such sets corresponding to each lambda. Corresponding to each lambda value. Okay. So I repeat that each of these lambdas are the eigenvalues and each such set of n1, n2 and 3 are the eigenvectors, is the eigenvector. Alright, so going back to our original question, so these eigenvalues will give you the different possible extreme values of the principal strains or the maximum engineering strains, and the corresponding eigenvectors. So each of these n1, n2, n3, so they will be providing you with the directions. You note that these n1, n2, n3 are also the direction cosines of the unit vector that you are interested in. And because we have worked for this derivation, we had to put in some work in order to ensure that that the constraint 1 minus nkk was ensured. So this they will be set up in such a fashion that they will be unit vectors. So n1 square plus n2 square plus n3 square should be equal to 1. All right. Thank you very much. So in the next part of the lecture, we'll be going on to the last topic of the kinematics chapter. Thank you very much.